conference room, and everybody that is online, except one. So, yeah, today we have the final exam for Miles. So the structure of the exam, just everybody knows it, but I'm just gonna remind you just in case. So we're gonna start with a short presentation about Miles' project, and then the people from the audience, both in here or online, are welcome to ask questions about his talk. And then when we're done with that part of the exam, we're gonna ask everybody to excuse us. We're gonna stop recording as well. And then we're gonna have a session with only the committee members for the last portion of the exam, okay? So with that, questions? Or...
Actually, I was just gonna make sure that everyone on Zoom can hear me.
Yeah.
Is that good?
Is everybody can hear?
Yep.
James?
We can hear.
Yeah,
perfect.
Yeah, there you go. Good. All right, James. So just whenever you're ready.
All right, thanks everyone for being here. So today I'm going to be introducing a kind of univariate extreme value analysis as a way of studying precipitation data. So before we get started, I kind of want to lay out a roadmap for what we're going to talk about. So I'm going to phrase this as a series of questions and answers, starting with, what are extreme precipitation events? I'm going to refer to as EPEs. What constitutes extreme? And for that, I'm going to give some context. Then I want to get into, if we know what EPEs are, what tools exist for actually studying them? And the answer to that question is going to be a sort of umbrella term that we call extreme value analysis. If we have the tools, then exactly how can these tools be applied? And for that, I'm going to propose a sort of general methodology. And then we want to know, okay, if we apply these methodologies to specific experimental data or observational data, what do those methods say about, for example, precipitation extremes here in Oregon? And for that, I'm going to present a case study. And finally, I want to leave you guys off with a question, so what? So without further ado, what are extreme precipitation events? So this is a very formal definition. This is not my definition. But it's pretty self-explanatory. An EPE is an event that is rare at a particular place and time of year based on the determination of some threshold, either relative or absolute. And that's actually not my definition. That is from the IPCC's recent assessment report. Now, for the statisticians in the room, you'd notice that there's already three things that kind of stick out about this statement, is that A, we are talking about extreme events, the tail end behavior or the low probability events of some kind of distribution, as opposed to the mean field behavior, which is typically what we care about. And more importantly, what constitutes extreme is going to vary over both space and time. And any one of these three pieces sort of constitutes its own realm in statistics. So having the intersection of all three of these things is going to propose some unique challenges for how we address the issue. As for studying EPEs, there's two main perspectives, either focusing on the changes in frequency and keeping intensity kind of fixed, or the other way around, keeping frequency fixed and observing changes in their intensity. And for this presentation, I'm going to be focusing mainly on the second one of these, talking about changes in intensity. So of interest are describing historical trends in EPE intensity and knowing how is that going to pan out in the future in a broad sense? Are EPEs getting more extreme or less extreme going forward? And how is that sort of going to inform our agricultural, architectural, industrial practices? So the good news is that there is a wealth of data available to us for meeting these goals. NOAA maintains a database of time series for weather stations, thousands of weather stations all across the US. And each one of these time series contains daily one-day rainfall totals for each one of these. And so you can imagine kind of slicing the data in two different ways, either spatially and mapping out values of these one-day totals for a given, a fixed time frame, or for any one of these stations, sort of inspecting them temporally and looking at how their time series sort of look in the long run. So we've got a lot of data, but the question is, how do we actually use it? Because the data itself is not straightforward. You see there's some challenges with it, and sort of the most obvious is the spatial and temporal dependency in it, right? If there's spatial and temporal autocorrelation, we have to account for that in some way as we're analyzing the data. The other thing is that the data is spatially and temporally incomplete. Now, the temporal incompleteness part of this is pretty easy to understand, right? If I look at this time series over here, there are gaps in the data, right? Not every day has every single measurement, and so actually taking summary statistics is going to require us to make some decisions about how we deal with those missing values, whether we omit them, whether we impute them, etc. The other part of this, the spatial incompleteness, is kind of the fact that when I'm talking about EPEs, I want to make a statement about Oregon in general, or about any particular place in Oregon, maybe where there's not a weather station. And so I have this sort of continuous Euclidean space, but the number of weather stations in that space is sparse. So at the end of the day, I'm going to have to do some kind of interpolation at some point to actually get a complete picture of what EPEs behave like in space. The third issue that is actually kind of one of the most important here is that the distribution of rainfall totals is not nice. It does not follow any kind of well-known exponential distribution or something like that. Namely, the distribution of daily rainfall totals is both extremely zero inflated and extremely heavy tailed. So if I actually take a time series like this and summarize it with a histogram, what I get is that the vast majority of days, there's no rainfall or so little rainfall that it can't be detected by a rain gauge. There's a lot of missing values, and there's a small percentage of values that are very extreme relative to the rest of the days. So if I don't really know what the underlying distribution is for precipitation data, how can I deal with that? And the answer is, or to that, to the answer to that question of what tools exist for actually studying EPEs, the answer is a set of tools we call extreme value analysis. So the first main approach where we're fixing frequency and sort of studying intensity, this approach is typically referred to as the block maxima approach. And the idea is that we're going to take some poorly behaved series, like daily precipitation totals. We're going to summarize them into a well-behaved series, by which I mean it's easier to model, that the distribution is known, ideally, but we'll still capture that information about extremes. And the block maxima is sort of the most natural approach to this, where I'm going to take some temporal span, I'm going to split it into chunks, and just examine one single value within each one of those chunks, namely the maximum. So visually, I can take my time series, I can take these temporal blocks of 1 year, and then within each one of those years, just get the block maximum. And these red dots are going to summarize my data, capturing all of the information about low probability events that I'm interested in, and also give me some very nice properties. So I said that the block maxima series is well behaved, but to be more specific, what I mean is that if these blocks are large enough, like the span of a year, then the block maxima should have a couple nice properties. One, they should be temporally independent, right? They should also be robust to minor temporal incompleteness, right? If these blocks are a year long, then missing a couple of values like a day or even a whole week shouldn't usually have that much of an impact on what the actual sample maximum is. But the best part of this is that the block maxima approximately follow a known distribution. So the sort of keystone in all of this is this asymptotic theorem known as the first extreme value theorem. You might also see it under the name of the Fisher-Tippett-Nedenko theorem, more formally. And what it says is this. If you have an IID sample of random variables, and the distribution of the sample maximum converges as the sample size increases, then it must converge to a generalized extreme value distribution. Now, in theory land, we have to be careful about not talking about like converging to a moving target. So the way to formalize this is we talk instead about the normalized sample maximum. We say, if you have an IID sample, and there exist normalizing sequences AN and BN, such that the normalized sample max converges in distribution, then that limiting distribution must be from the GEVD family. So we've gone from having this original time series, which has very unknown properties when it comes to its distribution, to having a summarizing series, which we can make statements about, as long as our block sizes are large enough. So natural question is, what is a GEVD, right? How does that actually look on paper? So taking a step back and talking about just a single random variable for a moment, the GEVD family it's a 3-parameter family, location scale family, but its qualitative behavior depends kind of most importantly on the shape parameter, where if the shape parameter is positive, negative, or equal to 0, it's going to take on one of these 3 other distributions. So very commonly, we see the first extreme value theorem said in a different way, not in terms of the GEVD family, but in terms of just these 3 families here. Now, if I'm interested in knowing how the block maxima change over time, for example, or over space, I want to know, in other words, how did these parameters, the location, scale, and shape, change over time and space? And so now I don't have to talk about the extremes of the original precipitation time series. I can just talk about the parameters of this new summarizing time series, which is a lot easier to do. And the beauty of this is that I've completely defined the distribution asymptotically, right? If I know what the distribution of the block maxima is, I can tell you about its typical behavior, about the spread of it, and most importantly, for climatologists at least, is what we call return levels, which is just the value a sample maximum is expected to exceed with probability p in any one particular year, which really is just another way of saying the 1 minus p quantile. And so typically, if we have a multiple of these block maxima, and they represent a block maxima series, we can frame return levels according to a return period, which is typically more digestible for non-statisticians. And so we can relate the return period and the return level in this way. So if we have a return period of t years, which is fixed, I get to choose it, then the return level is the 1 minus 1 over t quantile of the GEVD. So for example, the block maximum value for a 1 in 20 year event is just the 95th percentile or 0.95 quantile of the GEVD. So when I've got this individual weather station, and I've just got this one block maxima series, I've got all these nice properties about it. I can tell you all about its behavior and its change over time with some simplifying assumptions. So I've kind of at least partially solved a lot of these previous issues for a single series. So for an individual weather station, the extremal and temporal nature of the problem have been greatly simplified. And additionally, I have a probabilistic way of talking about how extreme the block maxima can get, how intense they can get over some time span through these return levels and return periods. So the question is, if I have this really nice approach for a univariate situation for just one single weather station, how can I actually apply that to EPEs in general, which are spatial in nature? And the simplest kind of naive way to do this is answer the question how these tools can be applied is through a univariate and combined methodology. The general framework looks like this. For each station, we basically get the block maxima series, typically annual maxima. We get that summary series, and then we make some simplifying assumptions about how that maxima can change over time. So if you think about it for a second, we don't make any assumptions about how the original daily precipitation time series behaves. It could be non-stationary. It could be that there's some sort of increasing trend over time, for example. And that non-stationarity should get carried over into the block maxima series. So even though these block maxima will be independent, they won't necessarily be identically distributed. Their parameters could change over time. And so we want to make some simplifying assumptions about those parameters so that we can have a tractable problem. Once we have made those assumptions, we can estimate a couple of them and then generalize those to a spatially complete grid through some kind of interpolation method. And then, although this is incredibly vague, once we have done that interpolation, we can get some estimate for our uncertainty in that interpolation. This is intentionally incredibly vague because how we do that depends a lot on the interpolation method that we use, right? If my interpolation method is very simple, like linear or bilinear or bicubic or something, it's not statistical in nature, then really what I have is just interpolating a bunch of MLEs, right? And through like the asymptotic normality of MLEs and like the delta method, getting standard errors can be kind of easy in those simple interpolation methods. Once I start using more intricate interpolation methods, obtaining standard error estimates becomes a lot harder. So this whole presentation and this sort of framework is inspired by a paper from Mark Visser and his colleagues at the Lawrence Berkeley National Lab. He's a famous climatologist, and he recently put out this paper, a probabilistic gridded data product, which is just a fancy way of saying interpolated data product for daily precipitation extremes over the United States. And in this, he basically takes that general framework that I just described and gets a little bit more specific about what he does and chooses the interpolation method very cleverly. So what he does is he says, okay, for each station S, we're going to get the block maxima series. In this case, what we're going to do is we're going to focus on one season at a time. In this case, maybe just winter. And so we're going to have a winter block. We're going to have a gap, 9 months, and then another winter block. And within each one of those winter blocks, we're going to consider the maximum. And consider that block maximum series from 1950 to 2017. We're going to get this block maxima series, and then what we're going to do is we're going to, bearing in mind that this time series could be non-stationary, make some assumptions about how they change over time. Namely, that the location parameter varies only linearly. So instead of having a location parameter for each time step, we just have a location intercept, kind of speak, and a location slope, kind of speak, to say that there's an initial location parameter at the start of the time series, and that changes over time linearly. And then we're also going to make the assumption that scale and shape do not change over time, so that all we have is really this additive shift in the distribution. Then all I have really for each weather station is 4 parameters to estimate, these 4. And if I obtain them using like maximum likelihood, I can reasonably model them over space using a Gaussian process. So I'm going to spare the details because this presentation is not all about interpolation methods, but the interpolation method that they use is a non-stationary anisotropic Gaussian process model, which basically means we're going to make very few assumptions about how these MLEs are related over space. So the spatial dependence could depend on where you are, as well as the direction in which you're facing, which I'll kind of elaborate on in a second. Now, the issue with this interpolation method is that it's really complicated. So not only is it incredibly difficult to explain here, but also how you obtain standard errors for your interpolation estimates is pretty complicated, right? We don't have an explicit formula for them. So what we have to do is we have to get them computationally somehow, or come up with another way. And so what they do is basically just bootstrapping. Steps 1 and 2 are actually not that computationally expensive. So what you can do is just repeat steps 1 and 2 1,000 or 10,000 times with block bootstrap samples of the original series, and then use that to obtain bootstrapped standard errors. Now, the next thing is, once we've actually interpolated these parameter estimates, we can have already interpolated maps of all the other quantities we'd be interested in, like the mean field behavior of the maxima, or in many cases, the return levels. So you can see measuring rainfall. I don't have a scale on here, that's my bad. Blue, darker blue is going to be larger values of this 20-year return value. And darker values are going to correspond to larger standard errors. What you can see is that we can get nice interpolated estimates for the return values and quantify our uncertainty spatially. So we can say, okay, even though we think the return values are going to be larger in the Pacific Northwest and generally west of the Cascades and west of the Sierra Nevadas, our uncertainty is also going to be pretty high in those areas. The other thing about their methodology for interpolation is that it gives us a really nice, interpretable, but also nuanced understanding of the spatial dependence between maxima. So here, This is actually a heuristic representation of the spatial dependence inherent in the data, where the directionality of these ovals sort of correspond to the directionality of the spatial dependence, and the length of them correspond to the sort of magnitude of spatial dependence. So like here in the Pacific Northwest, west of the Cascades, we have a strong north-south sort of spatial dependence where if I know what the typical values of the block maxima are like in Portland, I could probably tell you what they're like in Seattle or in Corvallis. But it would be pretty hard for me to generalize that same thing to something east of the Cascades, to Bend, Oregon, for example. So we have some general methodology and we have some specific applications of it that hold water. So the question is, if I actually apply these methods to my own observational data, what can I learn from it? So what I did is recreated the first sort of step before interpolation that Risser uses in his paper to a subset of the data that he uses. So specifically, I limited the spatial scope to just Oregon and limited the temporal scope from 1979 to 2017. So smaller data set, but focusing on locale. And so in this case study, I for each one of these weather stations performed that univariate extreme value analysis. And what we can see is that it seems like the location parameter, or at least the starting location parameter, is generally higher west of the Cascades. Go figure, that's nothing special, that's nothing new. What's a little bit more interesting is this location shift parameter here, or the location trend parameter. And the signal is kind of mixed, but it seems like generally the strength of this location parameter is stronger west of the Cascades, indicating a stronger change over time compared to east of the Cascades. You can see the signal is a lot more muddied east of the Cascades. Now, the location intercept, the location's shift, and the scale parameter are all measured in millimeters. So these are all fairly interpretable in terms of actually saying, okay, for these here up in Portland, typical values of the block maxima series are around somewhere between 50 and 75, give or take, millimeters in one day. Another way to kind of slice up this result is by looking at actual specific distributions and looking at them directly. So I've got 4 select locations here, kind of trying to get a good representation for the 4 corners of Oregon. So what we have is a weather station in Portland Airport and Medford, which show that their estimated GEVD densities have shifted or increased generally in value in the last 30 years. So the blue lines here are the estimated densities in 2010 versus the red lines are the estimated densities in 1980. We see that there's been a noticeable shift, a noticeable increase in typical values in the last 30 years. Versus in Baker City, which is in the far northeast, and in Redmond, which is kind of near Bend, it's kind of been the opposite, that their extremes are getting less extreme over time. Now bear in mind, based on the last slide, that signal is still pretty muddied before we interpolate any values. So if that Portland Airport station was this, that location shift that I just showed you would vary considerably from the next stop over. So again, that's not trying to be rigorous in my saying that extremes are getting more extreme, just a demonstration. So the question is, so what? Right? What do I care? So before I answer that question, I kind of want to recap of where we've been, right? Bottom line, describing EPEs is difficult because of the spatio-temporal and external nature of the problem, right? And the only, or sort of the easiest approach to dealing with them is to collapse the issue down to only 1 or 2 dimensions, so to speak. So as opposed to focusing on space and time and extremes all at once, kind of focusing on this univariate approach, and then simplifying the issue to just an issue of spatial interpolation. Now, bear in mind that the greatest challenge with this is that spatial interpolation step, right? Spatial interpolation is not easy. Lisa Madsen can agree with that, I would imagine. So
Prediction is hard.
yeah. So even though this seems like a straightforward approach, it still has its issues, right? Spatial interpolation constitutes its own field within stats, and your end results are going to be ultimately limited by that spatial interpolation method that you use. And recently, applications of this sort of univariate and combined approach have been demonstrated to actually produce interpolated products that are less noisy than previous methods. So the lessons learned, I would say, are this. Analyzing extreme behavior usually necessitates answering analogous questions, not looking at precipitation directly, but looking at a summary of precipitation that still captures the relevant information. That's kind of true for a lot of problems in stats, right? But more generally, this univariate and combined approach is not specific to precipitation data, right? A lot of the time series that we deal with are tricky and the underlying distribution is not known. So you can imagine if you're interested in health sciences, understanding extreme reactions to medication could be something that varies over both space and time. And although most people will have a reaction to a medication, whether that's blood pressure or heart rate or whatever, it's within a normal range, there will always be a handful of people who respond very extremely to medication. And understanding when and where that happens is important. Similarly, if you work in insurance or financial losses, right, you want to know, are the losses getting more extreme over time? Are they getting less extreme? Where and when is that happening? And generally, you could imagine extending this approach beyond a normal, like nice Euclidean space, right, to something where the spatial relationship is not determined based on geography, but based on something like a network, right? So you can imagine having a network of like websites, for example, and you want to understand how does traffic between these websites sort of flow typically, and how does it flow in the most extreme cases, right? Then use that to inform questions of, okay, what does my server need to have reliable uptime or things like that. And the last thing I think we should all take home is the asymptotic results are your friend, right? If you like the CLT and you like general asymptotic results about the sample mean, you should also like the first degree value theorem, and you should know it. So
That's right, transitivity.
Other questions?
Thank you. So we are gonna take a question from the audience. Maybe you should put
That's a good idea.
Is there any questions online on Zoom? Please just type them in or just you can just jump in and talk. Are there any questions here? No?
It was that clear.
Either one extreme or the other.
Your first graph that had like the days of precipitation, it looked like most days it doesn't rain, and is that for Oregon?
So that particular location was east of the Cascades,
Right.
where the extreme precipitation issue is not in too much rainfall, but too little, which, this methodology does not really address.
Say something in the chat.
Thanks, Mark.
Keith has a question.
Oh.
What was the question? How you know?
For block maxima, how can we be reasonably assured that a one-year block is sufficiently large to assume temporal independence? That's a good question. And there's really not a straightforward answer to that, just in the same way that there's not a straightforward answer to like, how many samples do I need for the central limit theorem to tell me that I have approximate normality of the sample mean, right? So, we use like a rule of thumb of like 30 for the central limit theorem, just because we can like run simulations and show no matter how funky the distribution is, 99 times out of 100, the sample mean still looks pretty normal, right? I haven't seen any studies that have come up or suggested a rule of thumb for extremes. And I think the big issue with that is that, first of all, the distribution of the block maximum is actually not guaranteed to converge, right? It's like if you use like the central limit theorem as like a comparison, the central limit theorem only works if the mean and the variance are both finite, right? We also have this similar constraint here where we need those normalizing sequences AN and BN to make this convergence in distribution work, right? And unlike the central limit there, we actually don't know what these normalizing sequences are in general. It depends heavily on the distribution. So the answer is, I don't know. But what I would imagine you could do is you could do something like bootstrapping or some other thing to resample from this original precipitation distribution to sort of get some idea for whether or not these are converging to a generalized extreme value distribution and how quickly that happens. You know, leveraging simulation with this particular data set.
Good. Is that okay, James, or you need to
Yeah, was
follow
that
up on that?
a satisfying answer?
Is it? Good answer. Okay, good. James approved. So, anybody else have questions? Yeah.
Maybe just one question, not totally understand the whole framework yet, but just in Oregon, it's like, for example, we during the past few years we have been very dry winter, but then suddenly this year we have many rainy days or snowy days. So your extreme value model is modeling the extreme within each year, right? And see how it's changing over. Do you consider the situation like what I just said? For many years, it's like one thing, then suddenly you have one big jump. Or
That's an interesting question. And so I don't think, so like when we make the assumption that like the location parameter changes over time linearly, right? I don't know that there's any way to sort of incorporate more complicated assumptions into that, such as like a sudden change in the time series, like a sudden shock. So when it comes to like parameterizing the model in a way that it accounts for something that complex, I don't know how you do it. Maybe with like an indicator function that depends on the year. And you could still use MLEs, I think, to estimate those. But I'm not totally sure.
but if you have a linear component, I suppose it's not too hard to make at least smooth function is not hard, right?
Yes, I
You're
can.
not adding maybe a couple more parameters.
Yeah, and so I think
yeah, what I said is more difficult. If there are like big changes, then it's difficult.
And so I think the value of having a very simplistic assumption like linear change over time is the interpretability versus, you know, if you use a general, you know, spline or some other general smoothing function, the picture of how it changes over time is going to be a lot more difficult to understand.
I'm happy.
Anybody else from the room in the room?
We do have a time, a short time.
Yeah, that's what I want to wrap up, right? Everything here, so, yeah, so then we're gonna stop here, like the public component of the
Thanks for coming, you guys.
right of the exam. Thank you, everybody, for joining. To let you guys know soon. Yeah. Yeah, stop sharing and stop recording. I got it. Stop everything.